So in this video we're going to calculate the projection of u onto v in a concrete case. So it says find the projection of u onto v and the component of u orthogonal to v for the vectors u and v that are given. And what we want to remember is the concept is that if we're taking a vector u and projecting it onto a vector v, the idea is that we draw a line through v, and then from the terminal point of view we drop that perpendicular to that line, and then our projection vector, if I change my ink color here, pointer options, ink, let's go switch over to black. The projection is the vector that starts here at the toe of u, runs parallel to the vector v out to the foot of that perpendicular. That vector right there is the projection of u onto v, and then the vector that goes from the foot of the perpendicular up to the terminal point on u is the component of u that is orthogonal or perpendicular to the vector v. And in the previous video we called this guy w sub 2, and then what we identified was that the projection plus w sub 2 has to add up to u. So if we do u minus the projection, we get the orthogonal component. So we want to remember that w sub 2, the component of u orthogonal to v, we get that by taking the vector u and subtracting off the component of u that's parallel to v. So we subtract off the projection of u onto v. So the orthogonal component is u minus the parallel component. So step one is to calculate the projection vector. So the projection of our vector u right here, right here onto v. From our previous results, it's going to be u dot v. So we do u, which is the vector 3, 2, and we dot that with the vector v, which is the vector 1, negative 2, and then we divide this by the size of v squared. But remember that the size of v squared is just v dot v from our dot product properties. So I can actually just take the vector v and dot it with itself to get the size of v squared. It's one way to do it. It's not the only way to do it. And then we multiply by the vector v. And the vector v is just the vector 1, negative 2. So we have a scalar times a vector is a vector. And then we just go ahead and run through the calculation. 3 times 1 is 3, plus 2 times negative 2 is negative 4, over 1 times 1 is 1, plus negative 2 times negative 2 is 4, equals 3 minus 4 is negative 1, and 1 plus 4 is 5. So we get negative 1/5 times, and then we should be pulling our vector down in each step. So this is the vector 1, negative 2. So this is the vector component that is parallel to v, the component of u parallel to v, or the projection of u onto v. And now to get the perpendicular component, we're just going to do the subtraction. We're going to do w sub 2 is the vector u, which is 3, 2, minus the parallel component, so minus the negative 1/5, times the vector 1, negative 2. And we have a double negation right here, so I can change this to a plus. And so this is going to be the vector 3 plus 1/5 times 1 is a fifth, so 3 plus a fifth, comma, and then I'm going to get 2 plus 1/5 times negative 2 is negative 2/5. And then we can simplify a little bit, so this is going to be the same as 15 plus 1 is 16/5, comma, and here we're going to get 10 minus 2 is 8/5. So there's the orthogonal component of u, And if we wanted to, we could factor out, we don't have to, but we could certainly factor out an 8/5. And if we did that, that would leave behind a 2 and a 1. I like to work with the vectors in factored forms because a lot of the calculations are simpler if you work through things in a factored form.